Every single morning, you reach for that tube of toothpaste without thinking twice. You squeeze. You brush. You rinse. But what if I told you that the simple tube in your hand is the product of one of the most sophisticated manufacturing processes on Earth? A process where a single mistake can contaminate tens of thousands of units. A process where precision is measured in milligrams. A process where technology rivals that of pharmaceutical and aerospace industries. Behind every tube lies a world of chemistry, engineering, and relentless quality control that most people never see. Today, we're going inside that world. This is how toothpaste is actually made. Brain Chapter 1, The Invisible Complexity, 045 to 215. Visual, toothpaste tube rotating on screen, then exploding into ingredient molecules. Look at this tube. It seems simple, right? Wrong. Toothpaste is one of the most complex consumer products you'll encounter. Think about what it must accomplish. First, it must clean your teeth effectively, removing plaque, food particles, and stains without scratching or damaging your enamel. That's a razor-thin balance. Second, it must remain chemically stable for up to 3 years. 3 years sitting in a warehouse, on a shelf, in your bathroom without separating, drying out, or growing bacteria. Third, it must work in extreme conditions. From the frozen tundra of Siberia at -40 degrees Celsius to the scorching heat of the Sahara at +50 degrees Celsius. Same product. Same performance. Fourth, it must deliver active ingredients like fluoride at precise concentrations. Too little, and it doesn't protect your teeth. Too much, and it can cause fluorosis, permanent white spots on teeth. Fifth, it must taste good. Because if it tastes terrible, you won't use it. And if you don't use it, all that engineering is worthless. And here's the kicker, it must do all of this while costing less than $5. This is why toothpaste manufacturing is not simple. This is why every step is controlled, monitored, and tested. Let's see how they do it. Factory Chapter 2, Raw Materials, Where Perfection Begins, 2:15 to 4 o'clock. Visual, massive climate-controlled warehouse with rows of ingredient containers. The story starts here, in a climate-controlled warehouse where temperature never varies more than 2 degrees. This isn't just storage. This is the foundation of quality control. The abrasive, the cleaning engine. The most critical ingredient? The abrasive. Usually calcium carbonate or hydrated silica, these aren't just ground-up rocks. They're precisely engineered particles, measured in microns. Each particle is 5 to 20 microns wide. That's 1/10 the thickness of a human hair. Why does size matter so much? If particles are too large or too sharp, they'll scratch your enamel like sandpaper. If they're too small or too round, they won't clean effectively. The particle size distribution must follow an exact bell curve. Quality control teams use laser diffraction analyzers to measure every batch. If the curve is off even slightly, the entire shipment is rejected. No exceptions. The humectants, moisture guardians. Next are humectants, glycerin and sorbitol. These molecules attract and trap water, preventing the toothpaste from drying into a rock inside the tube. Pharmaceutical-grade glycerin must be 99.5% pure or higher. Even trace impurities can affect taste or stability. The water, purer than you drink. Then there's water. But not tap water. Not even bottled water. This water goes through 5 purification stages. Pre-filtration for sediment. Activated carbon to remove organics. Reverse osmosis to strip minerals. UV sterilization to kill microorganisms. Final submicron filtration. The result? Water purer than what comes out of your faucet. Every batch is tested for bacterial count, dissolved solids, and pH before it's approved. The reality of ingredient control. Here's what most people don't understand. Every ingredient that enters this facility has a complete pedigree. Where it came from. When it was made. What batch number. Every test result. If a problem is discovered 6 months later, manufacturers can trace it back to the exact supplier, the exact batch, even the exact production shift. This level of traceability isn't optional. It's required by law. Balance Scale Chapter 3, Precision Measurement, No Human Error, 4 to 530. Visual, computer screens showing digital recipe, automated weighing systems. In modern toothpaste factories, ingredients are never measured by hand. Why? Because humans make mistakes. Computer-controlled batching. Instead, the entire process is controlled by sophisticated software systems. When a batch begins, the computer loads the exact formula. Ingredient list. Precise quantities, often to 3 decimal places. Addition sequence. Mixing parameters. Temperature targets. Quality checkpoints. Everything is specified digitally. Automated weighing. Ingredients are weighed using load cells, industrial scales accurate to 0.01%. If a formula calls for 125.00 kilograms of calcium carbonate, the system will dispense exactly that amount, plus or minus 125 grams. That's 0.1% accuracy. On industrial scales, weighing hundreds of kilograms. Sequential addition. The system controls when each ingredient is added. Stage 1, water and humectants, they form the liquid base. Stage 2, thickeners, they need time to hydrate. Stage 3, abrasives, added slowly to prevent clumping. Stage 4, active ingredients, added at specific temperature and pH. Stage 5, flavoring and colorants, added last to prevent degradation. Valves open.
The automated line
Pumps activate.
Precise filling.
Conveyors move.
Servo-driven arms.
All automatically.
Swiftly sealed.
All precisely. All recorded. Real-time monitoring. Throughout the process, sensors monitor everything. Temperature, plus or minus 0.1 degrees Celsius. pH, plus or minus 0.01 units. Viscosity, in Pascal seconds. Mixing speed, in RPM. Ingredient flow rates. If any parameter drifts out of specification, alarms sound. Production can pause automatically. This is how you eliminate human error. This is how you achieve consistency. Gear Chapter 4, Industrial Mixing, The Transformation, 5:30 to 7:15. Visual, massive stainless steel mixing tanks, close-up of mixing blades in motion. Now we enter the heart of the factory, the mixing room. This is where separate ingredients become toothpaste. The equipment. We're talking about massive stainless steel tanks, some holding 2,000 to 5,000 liters of paste. These aren't simple stirring vessels. They're equipped with multiple agitator designs, anchor, propeller, high shear. Temperature control jackets, circulating chilled water. Vacuum systems, for degassing. Inline sensors, monitoring everything continuously. The process, a choreographed dance. Mixing takes 3 to 6 hours. It happens in carefully controlled stages. Minutes 0 to 45, building the base. Water and humectants are added first. Mixed at moderate speed, about 50 revolutions per minute for industrial mixers. Temperature is critical. Too cold, and glycerin is too viscous. Too hot, and water evaporates. Then thickeners are added, slowly. If you dump xanthan gum all at once, it forms clumps that never dissolve. So it's added gradually, often through a high shear disperser. As thickeners hydrate, you can watch the mixture transform from a thin liquid into a thick, syrupy paste. Minutes 45 to 135, incorporating abrasives. Now comes the challenge, adding powdered abrasives without creating lumps or trapping air. Abrasives are fed through hoppers at controlled rates. The mixer speed adjusts based on viscosity. Multiple agitator types work together. Anchor blades scrape the walls. High shear dispersers in the center break up clusters. Propeller agitators create flow throughout the tank. The friction from mixing generates heat. If the paste gets too hot, it can change viscosity or degrade ingredients. So jacketed tanks circulate chilled water at 10 to 15 degrees Celsius to remove excess heat. Minutes 135 to 195, adding active ingredients. Once the base reaches the right consistency, fluoride is added. This is critical. Every person using this toothpaste must receive the correct fluoride dose. Quality control takes samples from the top, middle, and bottom of the tank. All samples must show the same fluoride concentration within plus or minus 3%. If they don't, mix longer. Test again. Minutes 195 to 225, flavoring and color. Finally, the sensory elements. Flavoring oils are incredibly concentrated. A 3,000-liter batch might use only 3 liters of flavor, that's 0.1% of the total. These are added last because they're volatile. Add them too early, and they evaporate. For striped toothpaste, a portion of the batch is separated, colored differently, and kept separate until filling. The goal. After hours of mixing, you have a perfectly uniform paste, smooth, glossy, dense, and consistent throughout. No lumps. No air pockets. No variations. Cyclone Chapter 5, Degassing, the critical hidden step, 7:15 to 8:30. Visual, paste under vacuum, bubbles rising to surface in slow motion. Here's a step most people have never heard of, degassing. And it's absolutely critical. The problem with air. When you mix thick paste with powders and liquids, air gets trapped. Not big bubbles, microscopic air pockets dispersed throughout. Why is this bad? Problem 1, air bubbles expand and contract with temperature. In hot warehouses, they can cause tubes to swell or burst. Problem 2, oxygen in trapped air can react with ingredients, causing discoloration, flavor degradation, and breakdown of active ingredients. Problem 3, air reduces density. Two tubes might look identical but contain different amounts of actual toothpaste. Problem 4, toothpaste with air bubbles comes out unevenly, with visible pockets or spongy texture. The solution, vacuum. After mixing, the paste is transferred to a degassing tank operating under vacuum. The pressure is reduced to 20 to 50 millibars, compared to normal atmospheric pressure of. Under vacuum, toothpaste paste is degassed so trapped air bubbles expand, rise, and escape. This step takes 30 to 90 minutes and ensures correct density, 1.3 to 1.5 g/cm superscript 3. If air remains, the paste goes back under vacuum. Consumers never see this, but quality depends on it. Next comes high-speed filling. Modern machines fill 300 to 600 tubes per minute. Tubes are aligned automatically, filled with extreme precision, plus or minus 0.3 g, heat sealed at 180 to 220 degrees Celsius, and inspected by cameras and weight sensors. Defect rate is kept below 0.1%. Every tube receives a batch code for full traceability. After filling, samples go to quality control labs. Tests include fluoride levels, contamination checks, bacteria testing, viscosity, density, abrasivity, pH, and taste. If even one test fails, the entire batch is destroyed. Approved tubes are then automatically packaged, boxed, palletized, and shipped worldwide. A single factory can produce millions of identical tubes per day. What looks simple on your bathroom shelf is actually the result of precision engineering, strict testing, and advanced automation. That's the hidden science behind toothpaste. Tooth sparkles.